Good evening, everyone. Welcome to the lecture. So today's topic is TD learning, temporal difference learning. Okay. Last class we studied about Monte Carlo approach, right? What we had to do in that was we wait for the entire episode to roll out, right? And then wait till the end of that episode to update your value function and the other parameters. TD learning differs in the sense that you don't have to wait for the entire episode to complete, right? You can do it after one step, okay? This is the main distinction. Now we'll get into the details. So that was basically the spoiler of the movie. This is one step, okay? That was the entire episode. Now, the base you remember was dynamic programming, right? For which which was used to solve or obtain the value function and then use policy iteration or value iteration to improve on that value function and thereby get the optimal policy. But for that, you needed a model, right? Monte Carlo eliminated the need for model. But it required you to complete the full episode because it was based on true returns, right? Not any estimates. There was no estimates. Therefore no bias. The variance was high, true, but then it dies down as well as you go towards the true value and the number of episodes or epochs increased sufficiently. This one, this method that we are talking about, temporal difference method, this you do not have to wait till the entirety of the episode to complete to update your value functions, right? So Monte Carlo, full episode. That meant real returns. Okay. TD learning, no full episodes. If there are no full episodes, can you get the real returns for that episode? So there is some kind of estimation, right? There is estimation. This estimation is called bootstrapping. Bootstrapping. Okay? You'll hear the word bootstrapping quite often now in this lecture. So just wanted to give you a heads up, okay? So temporal difference learning does not require a model as Monte Carlo. The similarity, the difference, here in TD learning, you do not have to wait for the entire episode to complete because you rely on the estimates. And what are estimates? Okay, GT is what? Return, right? Whereas V pi was value function, which mathematically was expectation. Expectation of that GT, right? Value function was nothing but an estimate, right? Which is mathematically defined as the expectation of the returns. So now, from this definition, you can understand that TD learning will use returns or value functions. Value functions. Why? Because we are using an estimate here as opposed to the real returns. Okay? Now, because we are using estimates here, okay, this expectation operator, the bias will be high initially, okay, but the variance will be low. Why? Because you assume that you start with an initial condition and you keep updating that initial condition gradually based on the expectations, right? The expectation will not change drastically, okay? Right? Okay. You people watch sports, I'm assuming, okay? When you see a match, say a football match, okay? You know two teams playing, okay? You know more or less their strengths, their weaknesses, how good is each team, okay? So even before the match, you have some kind of expectation, right? 10 minutes into the match, your expectation might change slightly, but not drastically, right? 20 minutes into the match, your expectation might change slightly from the your previous estimate, but a little more maybe from the starting estimate. So you see how over the 90-minute period, your expectations keep on changing gradually. It will not be a drastic change. If the time frame that you're considering is small enough, then the changes will not be very drastic. Hence, the variance will be small, right? But maybe your team, maybe the team that you thought would score more goals would end up scoring 0 goals, and the team that you thought will not score a lot of goals would end up scoring 4 goals, maybe, right? So your initial estimates can be very wrong, right? But eventually, over the cycle of estimation periods, it will converge to the true value, right? At the 90th minute, you will know exactly that, okay, fine, this team scored 3, this team scored 1. Okay? So you get the evolution of expectations, right? The estimations that you have. This is exactly what TD learning does. Okay? It's like, okay, let's wait. We do not have to wait for the entirety of the episode. After one step, we'll estimate this value, then we'll correct it, then we'll correct it, then we'll correct it, and we'll keep on doing it till the end of time. Okay? Clear? So here, your target value function is itself dependent or a function of another estimate, which is the value function of the next state, right? So what you do is in TD learning is you take your VPI to be the reward that you get for taking that action plus the discounted future value of the next state. Okay? This is exactly what it is mathematically, right? Your value function of your current state will be updated based on the reward that you get, the immediate reward that you get from transitioning from state S to S prime, and then on whatever your expected value function is, the discounted value of that expected reward value function of that state. Okay? Okay. With TD learning, you can work with continuous episodes, okay, or continuous tasks, or episodes which do not have any termination, so to say. Okay? How and why? Yes.
Why? Because it doesn't require you to finish a full episode.
Exactly. Exactly. Because we are using estimates here, so we don't have to rely or wait till the end of the episode, right? So that's why we can do it. That's why it's good for tasks that do not have any ending as well. Okay? Non-episodic tasks.
So TD0 is the same value function equation. It is the same one.
Yes, mathematically it is the same thing. This is TD equation, not TD0 yet. I'll come to TD0 in a few minutes. Or now, TD0 rather, okay. You see, TDN, temporal difference is usually referred to as in this form, okay? TDN. Now what does N here mean? N is the number of steps you will have to move forward, indexed from 0, okay? If you move one step, that becomes TD0, okay? Now assuming your N is the last step, or N is infinity, then it becomes TD infinity. Can anyone tell me what TD infinity is? True value. Therefore, if you have temporal difference situation where you have infinite steps, that equalizes to Monte Carlo. Because what was Monte Carlo? Where you're getting the true value. Right? Clear on this?
So N is the number of steps you take from start.
Yes, indexed by 0, like 0, 1, 2, 3, 4, 5. That's why TD0 means you're taking only one step. You're considering only one step into the future. Right? Okay. Okay, yes. Now you see there is the term called difference, right? Temporal difference. Meaning there is some kind of difference involved here, mathematical difference, right? What is the difference here? It is the difference between your actual estimate, okay, that you have, and your current estimate. It should be, yes, so it's basically your target that you have, that you want to reach, minus the actual value you have. This is the difference we are considering. Okay? So your difference here is your target value by your actual value. Now a very interesting thing here is your target itself is not fixed. Okay? As in, Okay, like I told you, the football example, we'll go back to that football example, okay? Say if 15 minutes after the start of the match, your friend asks you, okay, how close were you? Or how close were you to your predicted score line? Your predicted score line was for the final, for the end goal, right? For the end of the entire match. However, after 10 minutes, you see how the teams are playing and you update it a little bit. You're like, oh no, now my expected score line is 2-2, right? But as the match progresses, that expected score line will keep on changing. So your estimation error, if you change the window, if you consider the window that you're moving to, will differ, right? So your target is not fixed in that sense. For every window, it depends on the window, the target depends on the number that you have at the end of that window only, right? So this target in itself is changing, and so is the actual value.
What is target in the like? Isn't it like you said, we're bootstrapping?
Yes.
So we're after an estimate.
Yes.
When you say actual, that is the ground truth, right?
The ground truth we are getting, yeah. No, the actual value, okay, the current actual value rather, as in based on your computation. So you mean, what about the bias and variance in TD?
Yeah, how the
Okay, again, even in TD, okay, you have to do this over a pretty long horizon. The number of steps or episodes you have is pretty long. So the samples that you get are a lot of samples. So when you average over this samples, or when you repeat over that number of samples, you will converge to the true value. There are proofs for this one, for that theory, which I will not do it here, but then yes, there are proofs that will show you that even in TD learning, you will converge towards the optimal or the true values of the value functions. A good question you raised. That's the whole point. We are trying to eliminate this error. When this difference becomes 0, you will multiply the learning rate by 0, hence this entire term becomes 0. So your current estimate or your updated value function will be the same as the value function that you calculated. And at that point you have learned basically, reached the convergence. You get it? That's what we are trying to push towards. So at this point, your difference is something high, right? That delta exists. So you're trying to move to eliminate that delta. When you reach there, you realize, oh no, that's not the goal. There is a goal further away or some different place. Then you recalibrate, you move towards that. Again, you do that. You repeat that again till the actual value function is obtained. At that point, this entire term will be 0. Yes, RT plus 1. Because it's the reward that you get after you move from ST to ST plus 1. Which one? Here. Okay.
It's always R of S, not R of S plus 1.
Yes, R of S, this is T plus 1, not S plus 1. There's a difference between T plus 1 and S plus 1. So what did I tell about reward functions? The rewards that you get is the reward when you move from state S to state S prime. So you have completed one time unit here. It's not an instantaneous or a 0 time process, right? There is some time. So that time is T plus 1 here. Okay, it's not S plus 1, it's T plus 1. There's a difference. Yes, here also V is T plus 1. Because when you moved this, basically, this entire term is V of S. Okay, so what? Just a minute. This value that you see here is, say, V prime times V prime S, not Vs prime, V prime S, or rather V hat S. This is some estimate of this value function. There will come a point in time where V prime or V hat will be equal to Vs. At this point, the error cease to exist. It's 0. Okay? Exactly. It is that. right?
So is it an estimate of the same value function, not even in a ladder time step, like not like after an epoch or
After a step, not an epoch. An
be a
epoch
function?
would end up we having Monte Carlo.
Okay, okay, like entire bit
Yes,
growth. Okay, okay. So it is in t plus one, like that is the estimate of the value function after one time step. Like
exactly. Just one time step.
so, it's like
Reward
I'll show you. We'll do the numerical example. Okay, what is a sampled reward? Basically, a sampled reward is you define the, okay, you don't model the environment, but you have an environment, okay, because you are executing all the actions in some environment, okay. When in that environment you execute an action, you get some reward, okay. As in, if you move here, you will be like good or bad, or so that is the reward that you're getting. That is basically the sampled reward.
Bootstrapping means here like
Estimating.
In this example, we started with 0, 0, 0, 0 with all the values, then we are estimating in each value like it is good or bad, and based on this we are giving reward. This is the bootstrapping.
Bootstrapping is simply estimating. Like here, this part, this, where did it go? Okay, in that equation, I'll show you again. You have Vs prime, right? Which is this thing. You're updating the value function of the current state based on some estimate. So when you're using some estimate to update another estimate, because this still isn't your true value, right? You're still updating. So that is another estimate. That is bootstrapping. So yes, in TD, we are exactly doing what we are doing in DP, but we are estimating here. We are approximating here rather than the exact solution of the equations that we have. Clear?
mentioning using the probability, isn't it model free, the TD?
Which using probability? No. DP computes. DP is dynamic programming.
Yes.
Dynamic programming is not model free, right? Dynamic programming is the exact solution when you have the model, system model. TD is the model free version. Okay? Okay. This, like I said earlier, TD0 is one step, and if you have infinite steps, TD tends to Monte Carlo, right? Because you're getting the full returns. So here, you can balance the lambda here, okay? Lambda is this thing, TD lambda. Where did it go? I did not write, okay. You have TD lambda. So this lambda, you can increase or decrease to balance the bias and variance. This I'll explain now. Okay, I'll explain this now. Okay, so remember the difference between Monte Carlo and temporal difference? You are learning on the go. You're updating the parameters on the go. You don't wait for the episode to complete. Hence, it's online learning, okay? There's a different paradigm called on-policy learning, which is different from online learning, okay? I'll talk about on-policy learning after the example, okay? So yes, regarding the questions that you had about the guarantees of converging towards the optimal policy, yes, there are theoretical guarantees which show that if you approximate the value function using TD method, you will, with a probability of 1, reach the optimal values. That is guaranteed to reach the optimal values. Okay? Yes.
what is lambda?
Here I wrote TDN. It's denoted as lambda as well. Basically the number of steps that you have. Again, I'll probably re-explain it. Okay. So every time, no matter what policy, what algorithm you're following, you generate, or you rather log these information: state, action, and the reward that you get. Plus, where is the next state you end up in, and what next action you will take. You will have this tuple. Okay? You put this in a box, or rather in a logbook. You're like, okay, fine, you do it. You're following a policy. So say this is for pi1 at t1. Okay. Now, obviously, pi1 will have, say, till t100. That is, your pi will have 100 actions, assume. Okay. At t2, you will store a different block. t3, t4, t5, t6, till t100, you will log all this information. Okay. And if it is, say, TD approach, you keep updating your policy gradually. No, you keep updating your value function gradually. Okay, you keep doing that till you converge to the true value function. and then based on that, you extract the policy. Now in the next epoch, okay, you start with this updated policy. Let's say it is P1 hat, okay. Now when you're trying to again update your value function or your policy in turn, you cannot use this pi1 observations. All the observations that you stored for pi1 are immaterial now in on policy. In off policy, because the name suggests that you have to be on your policy. Basically, all the updates that are happening should be based on the policy you are. However, if you are following an off policy algorithm, in that case, what you can do is you can use the previous observations. You're like, oh, I still have this. Let me see this. No matter what action, what policy you had chosen, okay, you still have the same tuple. You're comparing, okay, like, okay, this was better. So probably the action corresponding to this one was better. I'll plug this into my policy now, right? Yes.
So in both policy, for example, what we look here, we take in the Q, for example, max over action, as we have done.
Well, all policies for that, all algorithms are that for that matter, if they are value based, okay.
Because we can look the previous. I mean, in this state to this state, we have like max the action that gives the max reward is X, Y, or Y, whatever.
Yeah, okay. In off policy, what you can do is you can still compare that. In on policy, you cannot even compare that. Is an algorithm based on TD approach, which is on policy. Okay? Okay, yes. Q learning is off policy. Yes, on policy. Okay. So, where was I? Sorry. SARSA, yes, okay. So, TD learning, what did we do by TD learning? What did dynamic programming do, by the way? Value function. How did you improve or how did you get the optimal policy? Through, what are the terms for that? We use two methods. Policy iteration and value iteration, right? No, policy iteration includes two methods, policy evaluation, policy improvement. So dynamic program is analogous to TD, where you at this point have only evaluated your policy or evaluated your value, yes, policy, which would in turn give you your value functions. You have just at this point reached till your value function, right? This is my optimal value functions. But you still don't have any idea about the optimal policy. SARSA helps you achieve that thing. It helps you achieve the optimal policy. Okay? SARSA is TD algorithm, based on TD algorithm for obtaining the optimal policy, and it is an on-policy method. Okay? SARSA, the acronym stands for state, action, next state, state action, reward, next state, and next action. Okay? Okay. So on policy, again, just to sum it up, if you are following a policy pi1 and improving pi1, then it is on policy. However, if you're following pi1 and improving a different policy pi2, then it is off policy. Because now you're doing whatever you're doing off the policy that you're following, right? If you are updating the policy that you are working on, then it is on policy. Okay? Is it?
If it's on policy or off policy, we're gonna always have SA, and then reward, and then S prime A prime.
Yes.
So
Yes.
why then are you considering SARSA on policy?
Oh, so you mean why does the name SARSA is taken by this SARSA algorithm?
So why SARSA is considered on policy given the name, the acronym? Typically, you know, the names convey a lot of physics.
Yes, yes.
All the physics, quite honestly.
Yes, okay. In that sense, yes, I get your point. But then for some reason which I'm not aware of, SARSA decided to take the name and be on policy. And whatever other methods they follow, like you find out a new name for yourself. I am SARSA. So it is, as far as I know, that's the thing. But yeah, okay. So in TD learning, what you are doing is finding V star, V pi, which would be V star, that is the optimal value function, right? But then remember when we did policy and value iterations, just calculating the value function was not enough. We had to do another step, and that involved the computation of, yes, pi, but before pi, how did you get to pi? Q, the action value function, right? Sarsa will do exactly that. Okay, you remember this equation where you had Vs will be Vs what you estimated plus the delta that you have. Sarsa has the same equation but for Q. And here the delta would be Q rather than V. Action space, yes, because you have to extract the actions in order to get the optimal policy. Right? Are we clear on that? Okay? Yes.
Just a small question. In the convergence graph, in on policy method, there will be initially high variance rather than off policy method.
Theoretically, that should be the case. Yes. Yes. Yes, okay. Again, just what I stated. You remember this equation was based on V's earlier. And because it was V is a function of only S, so you didn't have this A's there. Right? But because this is action value function, you have the A's involved here. Okay?
Hold on,
Yes.
the delta here should be, if you are to follow suit, it should be, look at the equation that you've written,
This one.
R plus gamma
Yes.
Q.
Yes. Minus Q.
Yeah, so it's missing R plus.
Oh, right. Okay. Minus Q. Sorry. Yes. 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 This is the TD term rather, and this is the TD difference, the entire thing. Okay. Yes. So yes, I didn't write the Q there. So this is the SARSA update rule. Now, in this, what you do is after you get the action value functions, you simply extract the maximum reward generating actions and stitch them together to get the policy pi. Clear? Again, here you remember the epsilon greedy method I talked about in Monte Carlo? To balance exploration and exploitation, you arbitrarily put a term called epsilon and you take the greediest action with the probability of epsilon and 1 minus the other way. 1 minus epsilon times you take the greedy action, epsilon times you take the exploring action, right? Okay. Now this exploration, like I told you, you cannot continue explore. Well, actually, you can. You can obviously continue exploring till forever, right? Okay, but that might not be the ideal thing. What you want to do is you want to explore till a certain point, and after that you want to reduce your exploration a little by little by little till it diminishes altogether. That's why usually we simply decay the exponential, the epsilon term over time. Okay, so as you progress over the epochs, the exploration goes down slide by slide by slide and completely vanishes when you're towards the end of the learning. Okay. Yes. So again, the properties are same as what we had for Q learning, sorry, for TD learning, where you have the optimality guaranteed, that is the convergence will be guaranteed to the optimal values, okay, over a fixed, like when you have infinite samples, you basically converge to the true value. So there is no bias when you converge towards the optimal value, okay. Variance is higher, like I said, higher than off policy, but it is still there. Not completely small as in GT, no, sorry, GT is higher. It is still there, but higher than off policy, okay. And robustness, yes, it is even in partially observable conditions, it will work better. That we'll talk about later. Sample efficiency, like I said, it is not as good as off policy, because in off policy you can reuse the samples that you have even from other policies to update your policy, right?